Okay, so the chat sessions will be recorded. They will be subsequently uploaded into YouTube, and then the link posted in Canvas for you to view later if you need to. So let me switch this camera around. We're going to go through the workbook sort of at the end of the chat session. So what I'm going to do now is share my screen. So can you all see the slides? Getting some thumbs up. Okay. So let me just the people that are shown as guests, if you can, try to download the Teams app onto your computer so that you can just automatically join these. But otherwise, let's go ahead and get started. So again, the primary focus of these chat sessions is to show you ways to solve problems in organic chemistry. So it's really meant to be an applied session. So if you have questions, you can either raise your hand in the little Teams chat thing, or you can type it in the chat box or unmute yourself and ask. Really, that's what I'm being paid to teach you. So if you have questions, you should ask them, because most likely other people have that same question. So for the first couple weeks at least, the agenda is going to look pretty much the same. I'll show a QR code for a molecule of the lecture, which we'll then look at, and I'll ask you some questions. We'll then look at that molecule of the lecture again, and I'll ask you these learn, explain, apply, predict, leap questions. So if we were face-to-face and I were writing the exams for you, those type of leap questions would be how I would write questions in the exam. Otherwise, your exams are going to be administered online through Wiley Plus, and I will pick questions from the test bank associated with your textbook. So if you're doing the Wiley Plus homework sets already, those are what the sort of what the questions on the exams will look like. So we'll do I don't think we have a think, pair, share. We have some sort of other questions about metacognition, basically, and then we'll get into the workbook. So here's the QR code for the molecule of the lecture. It's called amoxicillin. Okay, so you should have the structure up again. The nice thing about this app, this QR Chem app, you can visualize structure even if you don't have a model kit. You can rotate the molecule around, and basically, again, the point of this exercise is to show you that when we write things on paper, it's flat, but in reality, these molecules have shape, and the shape is imparted by the functional groups present in the molecule. So our standard intro question here, how many different elements do you observe in the structure? So you can, if you put the 2D structure on, basically it will show up sort of in the corner there. And you can actually see what those elements are. So here's the QR code. QR code again if you didn't scan it. So we have a new element in there that we didn't see before. So if we zoom in, you sort of see the yellow. So the yellow is typically denoted as sulfur. And again, in organic chemistry, we're looking at an abbreviated periodic table. So as we move across period 2, we have boron, carbon, nitrogen, oxygen, fluorine. Below oxygen is sulfur. So oxygen and sulfur are in the same group. They have similar reactivity patterns. So we're going to end up with 5 elements in here. We have carbon, hydrogen. We always have that. Nitrogen, oxygen, and now we have sulfur. So if if carbon is the gray colored atoms, how many types of CH3 carbons do you count? So how many CH3 carbons are there? And again, CH3, we denote that as a methyl group. So that's going to be important to us, is learning this vocabulary. CH3 is methyl. So yes, there are 2 methyl groups. And again, a lot of these questions are pretty straightforward at this point, because we are just learning how to analyze structure, classify carbon types, hydrogen types. But keep in mind, it's going to get more complex, because the reason I'm asking you to classify CH3 versus CH2 versus CH is that we will ultimately see, when we start learning reactions, we can selectively functionalize a CH3 group over a CH2 group over a CH group, depending on the reaction conditions. So again, if carbon is the gray colored atom, how many carbons are bearing no hydrogens? I think my multiple choice A, B, C, and D might not have the correct answer on there, so just put a number in the chat box. So I'm seeing more 6s than I am any other number, and 6 to me appears to be the correct answer. So let me show the slide here that has the structure on it. Again, sort of the first part of the chat session is a little bit of what we would call empirical research. You're examining that structure, asking some questions, and then we're going to dig a little bit deeper down. So here it is, the molecule of the lecture. The therapeutic indication is that it's an antibiotic. It's specifically called a beta-lactam in the penicillin class. Its mechanism of action, if you go on to take biochem and toxicology or pharmacology, MOA is mechanism of action. This molecule inhibits bacterial cell wall growth. So it's prescribed, you can see in the corner here, as a pill. Look at, you can sort of see it says amoxil and then 500. So presumably the 500, that's the dose, 500 milligrams. That's actually quite a bit of active pharmaceutical ingredient. Then you can see over in the left-hand corner, you can also dose this as an oral suspension. So for example, children can't really swallow pills that are that big. So a pharmacist will basically grind this material up, put it in some cherry flavored solution, and then you can dose the child. So let's point out those carbons that are not bearing hydrogens. So there's one right here. Remember, we called this a benzene ring. There's 1, 2, 3, 4. There's 5, and then 6. Let me briefly explain what a beta-lactam is. That's a functional group. It's this square-looking functional group. That's called a lactam. And again, I know you're getting this material sort of in dribs and drabs, but we'll have a screencast or two next week that goes through all these different functional groups, what the collection of elements in that functional group is, and what they're called. So this molecule was actually the source of the 1945 Nobel Prize in Medicine. So again, that's the societal relevance of organic chemistry in your studies here. And so these three gentlemen, Alexander Fleming, Ernst Chain, and Sir Walter Florey, each shared 1/3 of the prize for their discovery of penicillin and its curative effect in various infectious diseases. So we're all aware of COVID. COVID is an infectious disease. So these small molecules basically, let me just sort of explain sort of the differences you might hear in the news. This would not be considered a vaccine because if you get a bacterial infection, you'd have to take this pill to cure that infection. A vaccine is typically a large molecule, a large biological molecule. So if we added up the molecular formula of this, determine the molecular weight, it would probably have an atomic mass unit less than 1,000. Vaccines are typically in the kilo-Dalton range, so they're very big molecules. In organic chemistry, we only really are going to focus on small molecules such as this one. And one last thing before I leave this slide, as you can see, there's 1, 2, 3, 4 different representations of that molecule. This one is the one we would typically draw. If I were in lecture, that's the only way I could really draw it to convey the connectivity of the atoms to you, the bonding patterns. The one down here is a computer rendering of that same one. It actually starts to show you some shape. So see this ring system here, this 4-5 ring system. It's concave here due to the bonding pattern. This one here is called a ball and stick. So the atoms actually have sort of a spherical representation. And this one to the bottom right corner is called a space-filling molecule. The space-filling molecule is probably the most accurate representation of the molecule. So again, even though we communicate this way, you really in your brain should be thinking about the molecule in this fashion, because the shape of this, again, is what helps it, gives it this curative effect in humans. So let's transition into some more questions. And again, this is a question I wrote. If we were face to face and you were taking an exam that I wrote, this question would look like a question on that exam. So consider the structure of amoxicillin. Which of the indicated carbon atoms has the most hydrogens?
It's all right, yeah.
So how many hydrogens are on carbon A?
1.
1. What about B? 0.
Mm.
C? 1. And then D has 3. So again, what is this question asking you? It's asking about implicit hydrogens. So again, we said that carbon always has 4 bonds to it. So A, B, C, and D are all different bonding patterns of carbon. This is an sp2 hybridized carbon. It has 3 sigma bonds, 1 pi bond. This is sp2 as well, but notice now there's no hydrogens. We're explicitly showing 1, 2, 3 sigma bonds, and the 4th is the pi bond. C and D are both sp3 hybridized, meaning they all have sigma bonds. The implicit hydrogen not shown here, there's 1, and then here we have 3 implicit hydrogens. So you might need to break out a pencil or calculator at this point. Consider the structure of amoxicillin shown. How much mass does carbon contribute to the molecular formula? So what are you doing to solve this? You're counting the carbons, and then you're multiplying by the atomic mass of carbon, which is 12. So I see a lot of 192s. That's the answer that I came up with. So how did we get to 192? Let's identify those carbons.
1.
And so
Mhm.
again, in this exercise, what is the thought process that has to happen? We need to understand that we're representing bonds as lines. And where 2 of those lines meet at a vertex, this is considered to be a carbon. That's the convention that we use in chemistry. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So 16 times 12 gets us 192. Okay, so here's another different type of question, and this is related to functional groups. And I'm going to use this term unsaturated. That basically means an unsaturated functional group contains either a pi bond or a ring. So if you're looking at this structure, how many pi bonds do you see? How many rings do you see? And what's the sum of them?
Are pi bonds that are parts of rings included in this?
Can you repeat that again real quick?
Are pi bonds that are parts of a ring included in this?
Yes, every single pi bond. So I see a lot of 8s in C's. There's 1D, perhaps. I should maybe clarify something. So the shape hexagon, that is a ring. So any ring size, the minimum ring size you can have is 3. So there's one correct answer on here. Let me show you this. At the bottom right of that structure, you see CO2H. If you were to draw out that collection of atoms, it would look like that. So let's first count the rings. There's 1, that's the benzene ring. We have this lactam ring, a 4-membered ring, and then we have this 5-membered ring. So that's 3 rings. Pi bonds, we have 1, 2, 3, 4, 5. And then this group has another pi bond. So the correct answer is 9. So what is another skill or lecture learning outcome that you need to be able to do? Sometimes functional groups such as this can be condensed. So this is called a condensed formula. So again, the top sort of writing here is condensed, and then this bottom, as I've drawn it out, that would actually be the bond line. So top is condensed, bottom is bond lined. So you need to be very fluid in how you interpret going from condensed to bond line and back and forth. Any questions before we move on? So Carly, yeah, maybe just send me an email about the screencast question. So I want to transition. I normally talk a little bit about this in the face-to-face lecture. I'll talk about this slide now. So yeah, let me just answer Dustin's question real quick. So if you look, part of that structure was drawn like this. The little ball there at the top, that's the rest of the molecule. I'm just abbreviating it. So how did you know the structure of the CO2H as drawn like that? So that's one of the skills that you're going to have to develop, is when you're given like CO2H, you know from the Lewis dot structures how much each element can contribute in terms of valence electrons. Then you have to bond them together in such a way that you're not violating any of the Lewis dot rules. So again, organic chemistry is sort of a catch-22 in the following sense. To understand it, you have to already know it. And then to know it, you have to understand it. So you're going to get things not necessarily either from your reading or from these screencasts or lectures. You can't really get it all at once and have it all click. You have to see it multiple times and go through repetition before you really start making the connections. And so that really transitions into this word here, metacognition, which is important to us in transitioning from Gen Chem learning to organic chemistry learning. So metacognition is defined as the ability to think about one's own thinking, to be consciously aware of oneself as a problem solver, to monitor and control one's mental processing, to accurately judge one's level of learning. And I'll be quite frank with you. there are students in this class that will seemingly just understand or get this material. And I think that's because they are aware of how they think, and they're able to process information very quickly. If you haven't really used this type of thought process, it is sort of a learning curve. You really can't be distracted. I'm easily distracted, and I can sort of know when I'm going off the rails a little bit. So maybe as a test of your own metacognition, if you live in Hattiesburg and you're close to campus, go on the Longleaf Trace, start over by the dorms there and start walking west towards Westover Drive and Jackson Road. Don't have your phone out, don't listen to music, just start walking. What are you thinking about? Are you observing the surroundings? Are you focused on something? Is there some issue that you're thinking about? How easily does your mind go from one topic to another? Can you just walk and clear your mind out? Organic chemistry, when you're studying it and reading the textbook, it really requires you minimize your distractions, because you have to make a lot of different connections. And if you have trouble making those connections, this class is not impossible. What you have to do is just buckle down and fight that. You have to work through it. So here's a couple more things. A heuristic: perfect is the enemy of good. Again, if you don't get it at first, do not be discouraged. You will get it. Here's another thing, Sutton's Law. A reporter asked this bank robber, "Why do you rob banks?" The felon responded, "Because that's where the money is." So the reporter was presumably asking for some other reason, and the felon interpreted the question quite literally. The money is in the bank, that's why I'm robbing it. The reporter was probably asking about, what is your pathology? The questions that you're going to be asked in organic chemistry are pretty straightforward. So in a sense, don't overthink them. Try to connect the concepts. And lastly, Woodward's aphorism, or Occam's razor. You might have heard of Occam's razor. Woodward's aphorism is, they teach this to med school students in their first year. When you hear hoofbeats, think of horses, not zebras. And again, what does that mean? You might think I'm crazy about talking about this stuff. That sort of gets to what's going on up here. Think of the simplest explanation possible. Don't make stuff up. That's again, if you're on the Longleaf Trace and you're walking, clear your mind and find clarity. So I'm going to put up a couple problems next, and we'll sort of see from the responses, do you find clarity when you're looking at these questions? These questions are not meant to trick you. They're very straightforward. They're meant to gauge your understanding of the material. So the compound shown below is called butane. This is the name. That's the nomenclature, the name. This is the structure as we would draw that. It belongs to a functional group called an alkane. It is a hydrocarbon. There's only carbon and hydrogen, and exists as a gas at room temperature. What is the molecular formula of butane? So from the chat, I'm getting a lot of D answers. D as in dog. C4H10. So does anyone want to chime in? What is the intent of me asking you this question? So again, let me sort of give a little bit of a teaching philosophy here. If we were in face-to-face and I were writing the exam, I would write a question like this. The intent of this question is to probe whether or not you understand that this carbon in this carbon, we're only showing one explicit bond. So each of these has 3 hydrogens. So 3, 6. This carbon and this carbon, we're showing 1, 2 bonds. So each of these has 2 hydrogens. So when you're looking at this, you need to be cognizant that there's implicit hydrogens. So we get a total of 10 hydrogens. You can count the carbons. There's 1, 2, 3, 4. So if you took this on the exam and you answered D, I could be confident that you understand what this representation means and how you can convert it to a molecular formula. On the flip side of that, if I were to ask this question, say, in the following sense, if you were given the molecular formula C4H10, which of the following structures could be an isomer belonging to that molecular formula? So in your mind, you need to think one way and another way. You don't want to be so focused on your thought pattern that you're sort of blindsided by how the question is posed to you. So again, here's butane. How many sigma bonds are present in this alkane? So I see more D's than I do any other answer. You might think as a student, wow, that he's trying to trick me. But again, I assure you that I'm not. This is it's a straightforward question in terms of, you know, why do you rob banks? Because that's where the money is. Again, you don't want your mind to fool you, because we're only showing 1, 2, 3 sigma bonds. Keep in mind that, yes, we're only showing the bonds between carbons, but there's also these CH bonds. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 sigma bonds. So again, I am not employed by the university to trick you, to fool you, or any sort of malarkey like that. I am here really to help you think and to help you solve problems. I realize most of you are not going to be organic chemists, and that's fine. But what I want you to do is to, when you're given a problem, you can see it one way, but you also need to be open to seeing it other ways. So we've seen the hydrocarbon series methane, ethane, propane, butane. The next homologue in the series is called pentane. What's the molecular formula of pentane? So I see a lot of C answers, and that is the correct answer. Let me ask you a question now. This is a metacognitive question. What is wrong with the molecular formula presented in D, C5H14? What is wrong with that? Again, big picture in life, it's not always about getting the right answer, but explaining why something else is wrong or not correct. So we see we have 2 extra hydrogens, too many H's, extra hydrogens, break the octet rule. That is correct. So I used the word, remember from a couple slides ago, I used the word unsaturated. If you look at methane, ethane, propane, butane, pentane, the alkane series, they're what we call saturated. So what does that mean? Like right now, if you were to draw methane CH4, ethane CH3CH3, propane CH3CH2 CH3, butane CH3 CH2 CH2 CH3, pentane CH3 CH2 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 CH3. Every carbon has a sigma bond to hydrogen. That's what we mean by saturated. So alkanes, yes, they are. The molecular formula, that's where I'm getting, as you see in the chat there. CnH2n plus 2. So alkanes have a molecular formula of CnH2n plus 2. So whatever N is, you're going to have 2N plus 2 hydrogens. Saturated means that the carbon has 4 sigma bonds. And in terms of the alkane functional group, each sigma bond is either to a carbon or to a hydrogen. So again, the reason you can't have C5H14 is because you're violating a Lewis dot structure. And if you understand that, that's metacognition. If you were to try to draw that out, you'd find that you're bonding, you would have hydrogens that have more than one bond. And metacognitively, you know that that's wrong because it violates Lewis dot structures. So what about, before we move on to the workbook stuff, what about the molecular formula C5H10? Is that a valid molecular formula? So we have some definitive yeses, we have some it could be's. So it could be pentene. So notice that name in the chat there. This question is first asking you about pentane equals C5H12. Pentene equals C5H10. So notice that as I put in the chat box there, it's very subtle, but it tells you a lot of information. An alkane ends in ANE and it is saturated. An alkene ends in ENE and it is unsaturated. So what do we mean by unsaturation? So if you look at those molecular formulas, C5H12 versus C5H10, that's a difference of 2 less hydrogens, right? So as you see in some of the answers, Aiden put cyclopentane. So if you have a carbon that does not have the maximum number of hydrogens, we say it's unsaturated. And the unsaturation can belong to either a ring or a pi bond. So if the molecular formula C5H10, if it's not saturated, we know it has one degree of unsaturation. So DOU, that's degree of unsaturation. Right now, we've shown in the chat box, we've written 2 names, pentene and cyclopentane, for this molecular formula. Is that the total amount of constitutional isomers for that molecular formula? So Aiden wrote another one, methyl cyclobutane, that is valid as well. So how you can really learn organic chemistry. We've presented to you something as simple as a molecular formula, C5H10. We've now come up with 3 different constitutional isomers, just through our own thought processes of how we can bond carbon to carbon, carbon to hydrogen. We've come up with 3. There's more that you can come up with, because again, you're trying to bond all those carbons and hydrogens together using either one pi bond or one ring. So as an exercise to prove that you can think through this, after the session ends, why don't you spend some time trying to draw out these different constitutional isomers? And in another chat next week, we'll talk about that. But that's good practice to really test yourself if you're understanding the material. I assure you there's many more. But other than that, let's transition into some of the workbook stuff. As sort of another prompt, growing up in my house, my dad had this sort of picture, and it's actually on a piece of wood. It says, "Pray to God," but on the bottom it says, "Row towards shore." So these 2 gentlemen here in a boat, and it's stormy. So this is meant to show you that even though mentally, if you think you've heard rumors, this class is hard, I can't do it, I don't understand it, I'm going to tell you that's all BS. So you will understand it. So they're rowing to shore. They have not reached the shore yet. So that transitions into grit. I do not understand this yet. Again, sometimes things just click, sometimes they don't. Things take time. I'm encouraging you to give yourself that time. Don't let your mental processes get so far ahead of you and get yourself discouraged. Give yourself time to let things marinate and understand the material. So what I want to do in the last 15 minutes is click my camera around here and go through some of these problems in the physical workbook that came with the bundle for the required course materials. So again, let me know if this looks clear to you. Hopefully it's, let me know if it's too dark, too bright, whatever. Can you all see, well, first let me, this is what the cover looks like. So organic chemistry, first semester topics. So there was a question from an email. So the contents here, the chapters in this do not exactly align with how they're named in the course textbook, but they sort of follow. So chapter 1 is bond line, 2 is resonance. So we're going to look sort of at 1 and 2 over the first couple of weeks here. So let's go to page 2. Thanks, Rosemary. So let's look at exercise 1.1. So it says, count the number of carbon atoms in each of the following drawings. So for this molecule here, how many carbon atoms do you count? So I see some 6s. And again, this is all about us getting on the same page and how we communicate structure. As I was talking to a student yesterday, or excuse me, on Wednesday, one thing I've started doing recently to sort of in my own research is I bought a schload of colored pens. And they sort of really help me think about things and draw my eye so that I know there's something more than if I was just writing in like black or blue ink. So the reason I bring that up, like in your eye, if you're counting that, that's fine. But what if you have trouble visualizing? So I'm just going to pick any carbon. It doesn't matter which one. I want to start right here. I want to put 1, 2, 3, 4, 5, 6. So that's our answer. So I encourage you to, in whatever way works for you, to draw things out like that, because it will surely help you in terms of understanding structure. So what about this one here, this molecule? How many carbons do you see? So again, yeah, this is 5. So it's probably easiest to just number these. So 1, 2, 3, 4, 5. Maybe let me pep this up a little bit. How many CH3 groups do you see in this structure? So there's 2. How many CH2 groups? I don't know if the chat refreshed from my first question. How many CH2 groups? So there's 2. How many CH groups? 0. How many C groups? So carbons bearing no hydrogens. So that's 1. So if we add that together, 2 plus 2 is 4 plus 1, that's 5. That gets us our total carbon count. Now let me go back and probe how did we end up with 2? What's the location, using this numbering scheme here, what are the locations of the methyl groups, the CH3 groups? Rosemary says the ends. Sarah says 1 and 5. James says 1 and 5. So 1, 5. What about the CH2 groups? Three and 4. And then the C, the quaternary carbon, as it were, is 2. So again, these are questions that, so is it still quaternary if it has a double bond? Technically not. I sort of use that interchangeably, but it probably should not be called a quaternary carbon. So those are things that, even though your eyeball is looking at a structure, you always want to be thinking about questions like that. So let's do some more. Lower on this page here, and I'm going to adjust the document cam. So let's look at 1.2. This structure here, how many carbon atoms do you see? No, we're doing 1.2 still. So it is 6. Let me write those out in purple here. My eyeball is drawn right here, so I'm gonna draw 1, 2, 3, 4, 5, 6. Let me ask you, before we move on to another one, let me ask you, can you guys, someone's asking about the slide. Do you see the workbook? I think a lot of people do see the workbook, hopefully. Super tiny. Yeah, there's, maybe that's a little bit better. I'm now taking I was numbering with my purple. I'm now going to use my pink marker here and ask you a different type of question. The molecular formula, as we just determined, has 6 carbons. But not all 6 carbons are unique. That means some of these carbons are the same. How many unique type of carbons are in this molecule? So I see a lot of 3s, and I can probably if I had to explain why someone was choosing 3, it's probably because you're seeing multiple CH2 groups. But let me ask you a question. Even though there's 4 CH2 groups, are those CH2 groups the same? So for example, as I have drawn here in 3 and 4, are carbons 3 and 4 the same type of CH2 group? Blakely says yes. Camille, James, Rosemary say yes. Does anyone disagree?
I'm sorry, I can't see which ones are 2 and 4.
So we numbered it 1, 2, 3, 4, 5, 6. Is it the glare? So the question is, carbon 3 and carbon 4, are they the same? The types do not deal with IUPAC. So let's backtrack. Let's do the same type of analysis as we did before. Oop, that should just be C. How many CH3 groups do we have in the molecule? Zero. How many CH2 groups? So it is actually 5 because this is a C8. Carbon 1 is CH2 because it has 2 hydrogens. How many CH groups? 0. How many, this should just be C. How many carbons without? There's 1. Yes, that's correct. So again, we do that, that equals 6. So those numbers match. Now the question that I'm asking you is carbon number 3 the same as carbon number 4? Again, they're both CH2 groups, but are they the same type of CH2 group? Matthew says no. Rosemary says no. So I'm going to use my pink marker here. If you're standing, if you shrunk yourself, honey, I shrunk myself to the atomic level. I'm standing on carbon 2. I'm this little pink dot on carbon 2. And I look out that way. I look out this way. I see carbons 3 and 6. They're both CH2 groups. I look further, I see 4 and 5. They're both CH2 groups. But notice I'm on carbon 2. It would take me the same distance to walk to 3 and 6. So 3 and 6 are equivalent. But the distance to 4 and 5 is different than the distance to 3 and 6. So 3 is equal to 6, 4 is equal to 5. But 3 and 4 are not equivalent, and 5 and 6 are not equivalent. So it's a matter of your perspective, and yes, it has to do with symmetry. In the symmetric plane, I'm going to draw it as a dotted line, follows that line down the molecule. So carbon 4 mirrors 5, 3 mirrors 6, 2 mirrors itself, 1 mirrors itself. So we're about out of time now for this chat session, but if you have the workbooks, go through these extra ones. Keep going through the rest of the workbook, and if you hit a problem you don't know, again, we can discuss it in the chat or you can email me. So let me just read this. If two are not double bonded, would it change? The way I interpret the question that you're asking, I can't really answer that because I can envision a lot of different things. But if two had a hydrogen and then carbon 1 was a methyl group, you would still use the same logic to solve those questions I just asked. So I know you all are busy. Let me just wrap up. Please log into the Canvas website, start doing the Wiley readings, watch the screencast, start doing your problem sets for your assigned homework. Again, we'll meet Monday on the chat session. If you have any questions over the weekend, shoot me an email and I'll try to respond as soon as I can. But other than that, I'm going to go ahead and turn the recording off. I will post this